So let's quickly go over a little bit about what we did last time. We started talking about infinite sequences. We had this list of important limits. And we also had a very important inequality that we looked at last time. And I use these double less than signs to represent something grows much smaller than something else. For example, ln n grows much smaller than root n. And if you wanted to prove that inequality, what you would have to show that the ratio of ln n over root n, that goes to 0. So at the moment, we're going to use sometimes this inequality. So anytime you have something to the left of this inequality divided by something to the right of that quantity, the limit will go to 0. We've already proven some of these things last time. For example, ln n over n, we did that one. And one tool we used a lot last time was L'Hopital's rule, and it was used a lot in most of these proofs, like the 1, 2, 5. We used L'Hopital's rule. So let's also take a look at number 6 and 7. And then we're going to prove a few of these things today. Before we do that, I promise you, we're going to look at some of the group activity questions. Okay. So we're going to show that a polynomial function always grows slower than an exponential function. Basically, we're proving one item from that big inequality that I gave you. If you look back to the inequality, polynomial functions, which are of the form, since we're talking about not x's but n's, a polynomial function, we can write it like this. A polynomial, we're talking about sequences. So instead of x, I'm going to use n. So something like, let's say, n to the k, where n is the variable and k is a constant. For example, it could be n to the third power. So k is a constant. It could be the third power, the fifth power. What we're saying is no matter what the power is, we're going to show that these functions will go slower than an exponential function. At the moment, let's just use a simple exponential function, something like y equals e to the n as an exponential function. Let's just use at the moment the sequence, call that b sub n equals e to the n. And I'm going to call this a sub n equals n to the k. So we're trying to show that a sub n grows much, much slower than b sub n. And the way to show this is we need to show that limit as n goes to infinity of the ratio of a sub n over b sub n equals to what? If a sub n is really growing that much slower than b sub n, what would you expect the ratio to be? It should go to 0 because the bottom is growing much faster than the top, right? So the ratio should go to 0. This is what we're trying to show. Now let's put in what our a sub n and b sub n are in this question. So limit as n goes to infinity. We're going to show that n to the k, where k is a constant, divided by e to the n, the exponential function with base e. We're going to show that this goes to 0. To make things a little bit easier, first think about this one, n cubed over e to the n, the third degree polynomial. As a matter of fact, this is not really a polynomial. To be more specific, I need to call it a monomial because there's only one term. But a polynomial would have the lower degree terms. And basically, if you have the lower degree terms, they're going to be negligible. The highest degree term will determine the behavior of that third degree polynomial. So it suffices just to look at that highest degree term. Okay. So in the case of n cubed over e to the n, as n goes to infinity, what do you get first of all? The top goes to where? Infinity, right? N cubed, if n goes to infinity, top goes to infinity. How about the bottom? Where does the bottom approach? That goes to infinity as well, right? So we're starting with infinity over infinity. So can we use L'Hopital's rule? Certainly we can, right? So let's apply it to the top. Take the derivative of the top. Like what would be the derivative of n cubed over here? A simpler example. Derivative of n cubed is 3 times n squared, right? What is the derivative of n to the k? K times n to the k minus 1. How about the derivative of e to the n with respect to n? Think of it as e to the x. What is the derivative of e to the x with respect to x? It is e to the x, right? So e to the n will have the same derivative as itself, which is e to the n. That's why I picked that particular base. Taking derivatives is so much easier. Okay, now we still have infinity over infinity, right? So take the derivative one more time. Now you're going to have k times k minus 1 times n to which power? K minus 2. So we're subtracting one more power, right? Over derivative of the bottom is still the same, e to the n. Do you see what's going to happen here eventually? Let's put like that, that, that. Think of, again, our simple example, n cubed. Okay, the first time you differentiate, you get 3n squared, right? You differentiate again, and what do you get? 6n. Differentiate again, what did you get? 6. So ultimately, when you differentiate the top over and over again, you're going to get just a constant on the top. But what is happening to the exponential function on the bottom? It's staying the same, e to the n, e to the n, e to the n. So eventually, you're going to have a constant over e to the n. And where does that go to as n goes to infinity? A constant over e to the x, let's say. That goes to 0, right? So eventually, this is going to go to 0. But the way I can write this is as follows. I can say this is going to be the same as limit as n goes to infinity of, basically, ultimately on the top, this k times k minus 1 times k minus 2. There's a special name for it. Are you guys familiar with this notation, k factorial? In case you've never seen it, like if I write 5 factorial, it's like 5 times, 4 times, 3 times. You go all the way down to 1. Right, those of you who've taken statistics have seen that before, like that one happens to be 120. So when you keep differentiating this, you keep bringing the powers down, like here you brought the 3 down first, then you brought the 2 down, and then you brought the 1 down, so you end up with 3 factorial. In general, for the k power, you're going to have k factorial. You lose your variable, basically, after k derivatives. And on the bottom, still e to the n. K is just a constant. As n goes to infinity, the bottom is growing, the top is a constant, the ratio is 0. So we've shown what we were trying to show in this proof. So in general, we have shown that the derivative of, the limit of a polynomial type of function divided by exponential function will always be 0. I just showed you to a specific base of e. You could prove it also like with 2 to the n. But what is the derivative of 2 to the n? It doesn't get a lot of press, the 2 to the n function, right? E to the n is the one you see the most. So what is the derivative of 2 to the n? Let's just make sure everybody remembers that. You multiply it with something. Derivative of 2 to the n is 2 to the n times ln of 2. In case, so you're going to have extra ln of that base appearing on the top, but still you're going to have a constant over e to the n. It will still go to 0. Okay, so that's just a quick reminder there. Let's take a look at this next one. How do we show that ln n always grows slower than n to a power for any k? That's the interesting thing, because that k could even be 1/2. K could even be 1/5. As long as it's a number greater than 0. So for example, ln n grows slower than the square root of n function. It grows slower than the cube root of n function. It grows basically slower than n to any power. How could we prove this? First, let's just write down what the claim is. They're claiming that ln n is much, much less than n to the k. So we're going to show that the limit of ln n over n to the k is what? If the bottom is growing much faster than the top, where would you expect the ratio to go? The bottom is growing much faster, just like the previous example we did. You expect it to go to 0, right? So we're going to show that this answer is going to be 0. When you first begin trying to prove this, you have infinity over infinity, right? Infinity over infinity, because ln n goes to infinity, n to the k goes to infinity. Just remember, k is a constant. It's a number greater than 0. Okay, if you have infinity over infinity, how can you find the limits, the answer to a limit question? We have infinity over infinity, guys. What's that? It should be a red flag for applying L'Hopital's rule, right? So differentiate the top, and what do you get? The derivative of the top is, what is the derivative of ln n? Pardon me? Derivative of ln n is, think of it as ln x with respect to x. What is the derivative of ln x? 1 over x. The derivative of ln n would be 1 over n. Okay, our variable here is n basically, so this is going to be 1 over n. Okay, how about the derivative of n to the k? We just did that previously. Remember, k is a number like 5. What is the derivative of n to the 5? Think of it that way. K times n to the power of k minus 1. Okay, now let's simplify this a little bit. I'm going to bring that 1 over n to the bottom. So now I have limit as n goes to infinity of 1 over k times. If you bring that n into the denominator, you have the following: n times n to the k minus 1. So I brought this n down, the n that was on the top. How can you simplify n times n to the k minus 1? If you're multiplying things with the same base, you add the exponents, right? The exponent here happens to be 1. So you add the exponents. What do you end up with? N to the k, right? So here we have then 1 over k times n to the k. N to the power of k. Okay. Remember, k is a number greater than 0. So k cannot be like -2. If k is -2, if it could have been -2, you would put it back up in the numerator, but it cannot be. K is a positive number. That ensures that this n to the k is going to stay in the denominator, okay? So now you have n going to infinity, but n to the power of a positive number is in the denominator. So where do you think this ratio goes to? 1 over n to a power, where that power is the positive number. It goes to 0. The top is a constant. The bottom keeps getting larger and larger and larger. So the ratio is going towards 0. So basically, this is like a blanket proof for all sorts of things. For example, if you were trying to prove ln n divided by, let's say, cube root of n, or ln n divided by n to the 1/5, ln n divided by n to the 7th. So no matter what the power is, we're seeing that ln n is going to grow slower than n to a power as long as they're positive power, and the ratio will go to 0. Okay, now you see that we're doing quite a few proofs in this section, and you might expect to see some proofs, so don't completely ignore these things, because you're going to see it. Basically, this chapter, the emphasis is more on abstraction skills, some proofs following logical arguments. So there will be, in the past maybe I haven't asked you many proofs questions, but in this section I might say show that. This question right here, for example, could be a possible test question. Okay, one more I want to show you, and that one is, let's see if it's in the notes. No, I'm going to put that in there in the bottom of this page. This is actually, I believe, our rule number, special limit number, the last one. What was the last one? Special limit. The limit as n goes to infinity of n to the n over n factorial is infinity. I'm going to show this one a little bit differently. I'm going to show the reciprocal of this, which is equivalent. Limit as n goes to infinity of n factorial divided by n to the n is 0. This is what I'm going to show. Same thing, because basically what we're saying is we're saying n to the n grows much faster than n factorial, such that the ratio goes to 0. Okay, so we're going to show that n to the n grows much faster than n factorial. And look at our inequality on the bottom here. I'd already given that to you, right? That n to the n is the fastest growing function on this list. It grows faster than n factorial. So now we're going to show that the ratio goes to 0. Okay, so let me go back to a new page. So this is what we're trying to show. Limit as n goes to infinity of n factorial over n to the n is equal to 0. Okay, so first of all, I'm going to write down what this is. So let me rewrite the expression. Limit, not even the limit, just what is n factorial over n to the n? Okay, n factorial over n to the n is equal to. Tell me how I can expand n to the n. What would that look like? basically you're multiplying n times by side, right? So it's going to be something like n times n times n. How many of these you have? N of them, right? In the beginning we have n to the n, so you have n times n. And on the top, what is n factorial? All the way to 1. And there are equal number of factors on the top and equal number of factors on the bottom. There are n of them, basically. Okay, I'm going to try to use a squeeze theorem. I'm going to try to make this less than something that I know, to find the limit. And this is also, I know, is greater than 0 because we're always talking about positive values, and it's always positive for these problems. So if I can make it between two things that both of which go to 0, then I can conclude that this quantity will have to be would also have to go to 0. So what can I make it less than? Let's think about that for a minute. Okay, the very first one here, look at them one at a time, like n over n. What is n over n? That's 1, right? So this is less than or equal to 1 times, I put the equal sign because n over n is 1, so it's equal to 1. How about n minus 1 over n? What can you tell me about that? Is it greater than 1 or less than 1? N minus 1 over n. Think of like 7 over 8. It's definitely less than 1, right? N minus 1 over n. So that's less than 1. So I can put another 1 on this side because, and now I'm using the less than sign basically. So I'm putting in 1 instead of that, instead of n minus 1 over n. And instead of n minus 2 over n, that's also less than 1, right? I can put another 1 for that one. Okay. All the way to the last one. In the very last one, I'm going to use the equal sign here. And I'm going to write the same exact thing as it is, which is 1 over n. So a bunch of 1s and then times 1 over n. So what I'm saying is basically, I'm saying the original question, n factorial over n to the n, is less than or equal to 1 over n. And it's greater than 0. Now, what do we know about the limit of this? What is the limit of 1 over n as n goes to infinity? Would everybody agree that's 0, right? The bottom grows and top is a constant. Well, so your quantity that you're trying to prove here is squeezed between 0 and 0. So what is the only way for that to be correct? So I'm going to put here greater than or equal to 0 because it's either 0 or greater than 0 based on this side. And on the other side, it's less than or equal to 0. So what is the only way we can get out of this dilemma? It itself has to be 0, right? So by the squeeze theorem, therefore, limit of n factorial over n to the n itself has to be 0. And there we have it. We have shown that n factorial grows much slower than n to the n. So n to the n is pretty much one of the highest or fastest growing functions that we're going to see in this class. So for example, looking back to that inequality, if you have, let's say, do this one without showing me any work. Just use that inequality, okay? Say you have limit as n goes to infinity of n to the n over square root of n, let's say. What do you think the answer would be? N to the n over square root of n. Infinity, right? As Chris suggested, because the top grows much faster than the bottom. Again, if you think of that inequality, root n is way to the left-hand side of that inequality. N to the n is all the way on the right-hand side. So the ratio of n to the n over root n is going to be infinite. The top grows much faster than the bottom. And pretty much anytime you see n to the n on the top, unless on the bottom you have things of the form like n to the 2n or something like that, in your most typical functions on the bottom and n to the n on the top, the limit was going to end up being infinity, basically. Okay. Then I had a couple more examples that I want to go over with last time. See if I can figure out where they were. Okay, on this page. We have done some of these last class. Here's an interesting one. I'm going to give you some time to think about these. Like I said, I have to do the file transfer, and I'm going to be right back. Okay, the first example is find the limit of this sequence, n minus 2 factorial divided by n factorial. And the bottom one is saying find the limit of n squared over 2n plus 1 minus n squared over 2n minus 1. The top one is of the form infinity over infinity. The bottom is of the form infinity minus infinity. Both of them, you have to get rid of the indeterminate form. So think about it for a little bit, and then we're going to go over the n. Any thoughts about the first one? Did you try to simplify it? N minus 2 factorial over n factorial. We're going to do a lot of work with factorials. Let's be very, let's get used to simplifying these things. For example, n minus 2 factorial. How could you write that out? N minus 2 times n minus, you keep subtracting one and keep multiplying. Okay, so the next one you subtract would be what? Basically n minus 2 minus 1, which is n minus 3, n minus 4. It will go all the way down to 1, as always, by the definition of a factorial. Okay, and the bottom it is n times n minus 1 times n minus 2 times. It goes all the way down to 1. Do you see a cancellation there? Everything after which point is going to cancel? Exactly, on the bottom after n minus 2, everything on the bottom will cancel with everything on the top, right? So we're left with limit of 1 over n times n minus 1. And what is that limit? Any thoughts? That's 0, right? The bottom is a polynomial type of function, second degree. The top is just a constant. The bottom keeps growing. Therefore, the ratio goes to 0. And how about the next one, part F? This was something we did the other day, but ignore G for now, just F. Yes, Joshua?
Well, first it was I took these common denominator and subtract the two fractions. So each common denominator is 2n plus 1 times 2n minus 1.
Okay. And on the top you will have n squared times quantity 2n minus 1 minus n squared times quantity 2n plus 1. Would everybody agree? Why are we even bothering doing this? Couldn't we just say infinity minus infinity is 0 or something like that? Absolutely not, right? Remember, that's one of the indeterminate forms, such as infinity over infinity. We cannot just say it's going to be 1, right? Infinity to the 0, we cannot just say it's going to be 1. We have to get rid of the indeterminate forms. That's why in that pursuit, we're getting common denominators here. But getting common denominators, simplify the numerator. Let's see what we get. Okay, so this is limit as n goes to infinity of, okay, I'm going to have 2n cubed minus 2n cubed. They're going to cancel, right? Then minus n squared and minus n squared over the same denominator. So it looks like we have negative 2n squared on the top. Would you agree with that? I didn't show all the work there, but would you agree? Yes, because when you multiply it out, this times that will be 2n cubed, right? And this times that will be negative 2n cubed. So those canceled. But then you have this times that, which is negative n squared, and this times that another negative n squared. So that's negative 2n squared still remaining on the top. And the bottom is basically 4n squared and blah, 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 right? The degree at the top is equal to the degree of the bottom. So what can you say about the limits? Because on the top you have negative 2n squared. On the bottom you have 4n squared plus what, it doesn't matter what else as long as it's of smaller degree than 2. So the answer is, once again, as Gracie suggested, negative 1/2. Negative 2/4, in other words, negative 1/2. So we got rid of infinity minus infinity by getting common denominators in this case. So we've seen a multitude of tricks basically to find limit questions, to summarize sequences. You can look back to your important limits charts, that table of important limits. You can apply L'Hopital's rule. Try to get rid of indeterminate form any way you can by rewriting a given expression. You can use that inequality. But if the question says show that, show your work, or don't refer to just the shortcut formulas, then you got to show a little bit more work. Then you cannot just say, okay, this is rule number 5. Then I want you to show the work. Now, one more thing before we go to infinite series, and that is finding the nth term of a sequence. This is going to get a lot of use later on in this chapter, so we might as well get some familiarity with it now. No, still not the new lesson. Still, we're finishing up the sequences. Because what we have here is sequences separated with commas. Like the first one is the sequence of numbers 1, 3, 5, 7. What I'm looking for is a generic term to represent these sequences. For example, the first one is all the odd numbers, right? 1, 3, 5, 7. What would be a generic way to represent odd numbers? Pardon me? M plus, like, start plugging like 1. 1 plus 2 is 3, right? And plug in 2. 2 plus 2 is 4. So you're going to get like 3 and up. But it's not going to necessarily give you an odd number. What is the generic pattern for an odd number? If you like, let's do the second one first. Even numbers. It's going to be easier to deal with. For the odd numbers. And how about the even numbers? The even numbers, always a multiple of 2. That's what the definition of even is in the first place, right? 2n. So when you represent even numbers, you can just say, by the way, this is one way your book is using to represent a sequence notation. You can write it inside braces like that. This is a generic term where n goes from 1 to infinity. This is one way to represent a sequence with inside braces. Another way is just to write the notation we've been using, like a sub n is equal to 2n. Where n equals 1, 2, all the way to infinity. And this one, the first one, we can call it b sub n, an odd number. An odd number can be written as several ways. It could be like 2n plus 1, 2n minus 1. Let's just go with 2n plus 1. But where should I start to make the initial point to be 1? What should my n be? You must start at 0, because if n is 0, you get 1. If n is 1, so starting at 0 and plugging in every natural number after that, you're going to end up with the terms of a sequence which are all odd numbers. Okay, I want to give you a few moments to think about the next few ones. I know these are not always obvious, but some of them are so much more commonly used. Like this one, I may have to tell you, because if you've not worked with a certain quantity, you may not have seen this before. Does anybody recognize these as special numbers? 1, 2, 6, 24, 120? Factorials, good. William saw the pattern. Because again, if you've not worked with factorials before, it's very hard to see it. But think about it. 2 is 2 times 1, right? 6 is 3, 2, 1. 24 is 4, 3, 2, 1. And 120 is 5 times 5 and below. Again, if you've never seen it, don't feel bad. You didn't guess this one correctly. But from now on, at least some familiarity with these numbers, 6, 24, 120. Again, this one is your 3 factorial. This one is a 4 factorial. This one is 5 factorial. So what is the generic term of the sequence? A sub n equals n factorial as n equals 1, 2, 3, etc. So the generic term is n factorial. By the way, there's something weird about factorials. By definition, do you know what 0 factorial is? Anybody who's seen this before? By definition, it's defined to be 1. Who would have guessed, right? It's so weird. But why did they do it that way? You know, in a similar way, why did they define b, a number to the 0th power equal to 1? Because to make certain rules work, like when you're adding exponents, you know, those rules of exponents would work better. So to make certain rules of factorials work, they define 0 factorial as 1. You may never need it, but if you do, there it is as some trivia information for you. Okay, I'm going to give you a little bit more time for the remaining 3 sequences. Can you guess what the nth term would be? Okay, just a correction that the sequence should be 1, 4, 9, 16. So the first one is easy, right? 1, 4, 9, 16. What is the generic term for that sequence? N squared, right? Again, this is one way to write it as n goes from 1 to infinity, or you could say a sub n is equal to n squared, where n equals 1, 2, 3, etc. So that's the square of the nth integer. Now, how would you write the next one? Negative 1, 4, negative 9, 16. Yes, William? Let's try to see if we get what we want, because the other one is going to be very similar, but just one change. The first term should be positive. Let's check to see if your suggestion works, okay? So your suggestion was let a sub n be negative 1 to the n times n squared, right? And you're starting your n at 1, correct? Okay, so if n is 1, is it going to be positive or negative? Negative, right? And 1 squared is 1, so you have your negative 1. If n is 2, negative 1 to the second power is positive, and 2 squared is 4, so we have plus 4, right? So it looks like this is going to work. So when you have negatives alternating, again, think of negative 1 to the n or negative 1 to the n plus 1. Like this next one. Any suggestions for that? Let's try the other option, negative 1 to the n plus 1 times n squared. Let's see if this works. If n is 1, what will be the power of negative 1? The power will be the second power, so it makes it positive, right? So that forces it to start with a positive number, right? That little n plus 1 does the trick, and you can plug the numbers. You will see it will keep alternating. I'm going to ask you just a few more here. Okay. Can you write the generic term for the following sequences? The last one was negative 1 to the n plus 1 times n squared. Right, negative 1 to the n plus 1 times n squared. To the power of n plus 1. No, n starts at 1 for the last one. Right. Here it is. Negative 1 to the n plus 1 times n squared, n starting at 1. Because you see, when you plug in n equals 1, you're getting a second power. That makes it positive, right? Okay, I'm going to give you one more. It's going to be a little bit more challenging, but now that you've seen different patterns, you may be able to get this easier. So the Chris's suggestion was to write it as n minus 1 over n. As long as you set n equals to 2, that's one possible answer. What else could we write? Exactly. N over n plus 1 is another way to write it. And where would you start your n in this case? Start at 1. Again, if you plug in 1, you get a half. Plug in 2, you get 2/3, etc., right? Okay, how about the last one? Let's call that b sub n. I could take two partial answers here. In other words, if you have a pattern for the top, let me know. Now, 2n would also have things like 6 or 10 or 12. We don't have those here. This is not just even numbers, but these are powers of 2, right? Oh, I'm sorry. I heard it 2n. Maybe I didn't hear it from you. Maybe I heard it from somebody else. So one suggestion coming from class is 2 to the n for the top. Would you all agree with that, 2 to the n? Let's try it. If n is 1, you get 2, right? If n is 2, you get 2 squared. If n is 3, you get 2 to the third, or 8. So the top is indeed powers of 2. Okay? How about the bottom? Now, to make the top true, you've got to start at n equals to 1. Now, we have that restriction now for the bottom also. Now, the bottom, we see the odd numbers. Any suggestions? Yes, Garrett? 2n. 2n over n. Just n. But we want, if you make it just n, it would be like 2 over 1, 4 over 2, 8 over 3. You know what I mean? Okay, one suggestion I heard is 2n minus 1. Because 2n plus 1 and 2n minus 1 are good patterns for odd numbers. You could even use like 2n plus 3. Depending on where you want to start. This one, we want to start at n equals 1, right? And if you start at n equals 1, if you had put a 2n plus 1 here, that would make it starting at 3. That would not have worked. So 2n minus 1 is the one that works.